Hello everyone, welcome to my YouTube channel. My name is Nguyễn Chi Hiếu, a mechanical engineer, currently pursuing a master degree at National Chungcheong University in Taiwan. Today, I would like to share with you my first video to explain how to calculate the shell thickness of a pressure vessel. This marks the commencement of a series where I'll be covering the meticulous design and calculation of pressure vessels according to ASME standard, specifically ASME BPVC boiler and pressure vessel code. Before we move into detail of my calculation, I would like to explain some notes. They are important in my Excel file. We use various types of data. Each of them is distinguished by a specific color. So the yellow color is designate the input data. They are the initial input used in our calculation. It could be from the customer request. The green data represent the values. Those are formulated by the order data. The blue data is determined or assumed based on design condition or the fabrication requirement. And the final one, the orange color, the data retrieved from database is defined by some specific inputs. Let's begin with the first parameter, internal design pressure. So this type of pressure is acting on the inner surface of the shell. I've set it to 2 megapascal. For more detail, you could refer to UG 27 Section A Division 1. So moving on to the next parameter, design temperature. So I select 100 Celsius degree. And the next one is MDMT, the minimal design metal temperature. So this value is set to minus 20 degree, and I'll create another video to explain this parameter in more detail. The maximum allowable stress. So to calculate this value, we need to select the carbon steel plate SA516 grade 70 is the material for the shell, and the desired temperature is 100 degrees Celsius, with just the cut over here. So by referring UG 23 Section A Division 1 and Section 2 Part D, we determine that the maximum allowable stress for this material is equal 138 megapascal. So the next one is about the joint efficiency. So this value is defined as 1. So this factor is determined based on the welding process. In our case of vessel, the shell is made up from single or multiple steel plates, and the edges of this plate are perfectly welded together. And suppose that there are no mistake or imperfection in this work, we can confidently set the joint efficiency equal 1. The next parameter is about the corrosion allowance, and this value is determined based on our actual needs. Our pressure vessel is designed to hold the water, gas, oil, or chemicals, and over its lifetime, these kinds of liquid can cause the corrosion on the inner surface of the vessel, and moreover, the external factors like rainwater and oxidation can potentially corrode the outer surface. So to account for this problem, we set the corrosion allowance for the calculation, and it equals 2 millimeters. Next one is about the inside diameter. This is one of the input for our calculation. and I've set it to 2000 millimeters. The next one is about the radius, inside radius. This one would be a half of the inside diameter, so it could be 1000 millimeter. So the next one is about the plate tolerance based on UG16. So this plate tolerance is the difference between the actual thickness of the steel plate, which be used for fabricating the shell, and the design thickness that I'll talk in this session. So according to UG16, this value must be smaller than 0.3 millimeter or smaller than 6% of the design thickness. So in this case, it's equal 0.3 millimeters. So the next value is about the minimum required thickness of a shell in UG16. This value is a constant value and does not depend on the size of your device, so it must be always greater than 2.5 millimeters. Required thickness at the longitudinal joint. So in order to make sure that you won't be confused between these two definitions, I'll remind that at the longitudinal joint we have the circumferential stress, and upside down at the circumferential joint we have the stress in the longitudinal direction. So the required thickness at the longitudinal joint in this case is from equation 1 UG27. It requires some parameters like the internal pressure, inside radius, maximum allowable stress, efficient joints, and the corrosion allowance. So the value here is about 16.62 millimeters, and the same as circumferential joint, we have the required thickness is equal 9.23 millimeters, and this one is from equation 2 UG27. So and the next calculation is about the required thickness. So this value is selected from 3 required thickness over here. The required thickness of the UG16, required thickness of the longitudinal joint, and the required thickness of the circumferential joint. So this one is equal longitudinal joint because this one is the maximum value. Next parameter is about the nominal thickness. So this nominal thickness is determined by both the required thickness we just discussed earlier and the commercial thicknesses of the steel blades in the market. So we have the standard thickness in the market for steel blade. It comes in from many different thicknesses like 14, 16, 17 or 18 millimeters. So in this case, the nominal thickness I select 18 millimeters, is larger than the required thickness. But in the reality, the actual thickness could be smaller because of the blade tolerance. So we need to calculate the finished thickness, and the finished thickness is equal the nominal thickness minus the plate tolerance. So 18 minus 0.3 is equal 17.7 millimeters. And finally, we need to check the safety condition for our design to make sure that our design is safe. So yes here means that our design is safe because the finished thickness is larger than the required thickness. So this is my whole explanation for pressure vessel shell thickness calculation. So please comment below if you have any question, or give me one like if you think this video is useful. Thank you for watching and see you in the next videos.